All right, so yeah, night everybody. So the whole point of tonight's discussion is generally, I guess, talking about the latest developments with AI or in the AI field, and generally around the topic of, um, you know, is increasing scale the answer towards AGI, so artificial general intelligence. So recently, Google DeepMind came up with two interesting papers, or two interesting pieces of work. So the first one being, let me see if I can share my screen. Hmm. Yeah, so the first one being Palm. So Palm, basically, if you guys know about GPT-3, it's really just an advancement on that. So if you remember GPT-3, it's a language model created by OpenAI. So one of the biggest language models of its type at the time. So that obviously came with a lot of fanfare because of all the impressive stuff it could do, such as generating sentences, it could write code, basically do anything language related. And the results were so impressive because of the stuff that it would generate in terms of the text, almost human-like in how it did it. Now, basically, there have been some improvements on that same language model architecture. So GPT-3 worked on made use of the transformer model architecture. The transformers are basically, in a nutshell, makes use of attention layers. I won't go in detail in terms of the technical aspect of that, but that's the idea. I mean, you guys can look into what attention layers mean, but that's the main core tenet of a transformer model. But it's basically been the de facto model nowadays. So any sort of language model task or language modeling task. But not only that, what the more impressive thing is the fact that it's not only just being used in language, it's being used for other modalities as well, such as in the computer vision space, which I think it's a good sign because I mean I've always said that if we're gonna get to AGI, we're gonna have to get some sort of unified architecture. So basically one model that can be used for any sort of modality. So before, back in the day, if you were doing computer vision, you would more likely go for something like a CN, convolutional neural net. If you're doing something like language, then you'd go for something like a LSTM. So there wasn't really something that could really work well for the both of them. So I think Transformers is taking us along that path towards that one unified architecture, one unified model that can work for basically any modality, any task. No, is that the answer? No, is that going to be the final model, or is that going to be a part of what AGI, that final thing that AGI is? We don't know. I certainly don't know. A lot of people seem to think we're already there. I guess that's something that we can have a discussion about. I mean, there have been some clickbait articles about how DeepMind things were basically at AGI's doorstep. And just a few more scaling iterations and we're basically AGI. But the thing that you'll learn um, over time, reading a lot of these clickbait articles, they fail to mention, a lot of the erroneous outputs that a lot of these models tend to output, which if it really did understand the language, and I must admit, the results so far have been quite impressive. But if it really did understand the language, in my opinion, it kind of makes me question whether it really understood the language of if it was basically outputting such or making such stupid mistakes, for lack of a better term. So yeah, it's basically an improvement on the GPT architecture. So I mean, there have been several improvements on it, such as the GLAM, Lambda model, GOFO. But yeah, so GPT-3 had like what, I think 175 billion parameters. Palm, so this new model, new language model, makes use of 540 billion parameters. Now, I think that they didn't really make much, I would say, innovations in terms of the model itself. So it's not like they use a new type of transformer or they created something different from a transformer. It's the same sort of decoder transformer architecture that GPT-3 uses. But they, from what I've read in the paper, the big innovation they made in this paper is how they train the model, which allowed them to train a bigger, more, well, allow them to train a bigger language model more efficiently. So using their Palm, their pathways system. So basically, they were able to parallelize the use of multiple TPUs or TPU pods so that they could train the model more efficiently. So from what I understand, they were able to basically split up the model across multiple TPU pods. TPU, by the way, is just the chip that they use to train AI models, or at least Google uses. But yeah, they were able to parallelize that amongst multiple pods. So they were basically able to train a larger language model more efficiently. I think that's what a lot of these companies nowadays are doing. Basically, they have more or less settled on the architecture, which is more or less the same transformer architecture from 2017, probably with a few minor improvements here and there, but that's the main overall architecture. And their aim really is just to scale it up. So just make bigger and bigger transformers, more parameters, more weights. Of course, with more parameters, the harder it is to train. So they've basically shifted from creating new algorithms to more or less trying to see how current day hardware can train these models more efficiently. So make it more practical to train them. Now, obviously, the resources that Google has at hand, we don't even come close to having that at hand. Because from what I read in the paper, they basically made use of thousands of TPUs. And yeah, if we were supposed to try the same thing, that would cost a whole lot of money. So another question we can debate is, is AI becoming less and less inclusive based on these new advances? Because I mean, if the answer is scale, does that mean then that basically we just become more spectators of what's happening instead of being able to be participants in what's happening in AI? Yeah, so we can, I guess, more or less start the discussion off there in terms of this notion essentially that if we basically scale these large language models, that will somehow or whatever we create will somehow morph into AGI. So that all-encompassing AI system that can more or less take on any task, has good language understanding, possibly pass the Turing test. Is that possible with current day architecture or just scaling current day architecture? But just kind of looking at some of the results, impressive results that Palm has outputted. So this is an example of some basically reasoning problems. So they're looking at the example on the left. So the prompt is basically says Roger has 5 tennis balls. He buys 2 more cans of tennis balls. Each can has 3 tennis balls. How many tennis balls does he have now? So before, the answer might look something like that. Answer is 11. But here's an example where it sort of shows you how it reasons it out. So this is output from Palm, by the way. So it's saying here that Roger started out with 5 balls, 2 cans of 3 tennis balls, 6 tennis balls, 5 plus 6 equal 11. which in a sense is kind of so there's always been this talk of neural nets being black box models. If the AI can output basically how it reasons about finding answers, and that I think will be a good step. Of course, one could argue that is this output that you're seeing here, is it really the AI reasoning about something, or is it basically just how it was trained to answer questions in that way, essentially? Yeah, so I guess let's start off here. Just generally talking about scaling large models and whether we think that is the answer, or that will basically bring us closer to artificial general intelligence. So I'll throw it out to where's Zoom? Yeah, give me a sec. I'm looking for Zoom. Zoom. Oh, yeah. I guess I'll throw it out to you guys. So what do you guys think? Do you think scale is the answer?
Well, I think that scale is important, but I don't think it's the only answer. Because for example, with the DALI 2, like I know it's not a language model, but with the DALI 2 model, it was algorithmic improvements that made it that much more impressive rather than scale, because the neural net itself is actually smaller than the original DALI, and it was trained with similar amounts of compute. So the improvements that we got in terms of like the generated images and all of those stuff are essentially all came from algorithmic changes. So well, scale is important. I feel like an argument could be made that we need better training algorithms.
Yeah, I think that because he said that this one was trained with like 500 billion parameters. I think it would be more impressive if it can produce high quality results with like far less parameters. If you get what I mean.
Yeah,
That's
actually a good point. I mean, one of the hallmark of the brain is its efficiency. So I mean, the brain can run on like a few watts of energy, but yet produce these impressive results. So I mean, if AI is somehow to model or trying to model the abilities of the brain, I mean, one of the hallmarks of the brain is its efficiency. And based on our current path, I think we're moving away from that. We're essentially trying to brute force, or it feels like that. We're trying to brute force our way to AGI. So we're just saying, okay, let's just slap more hardware. Let's just train bigger and bigger models. Of course, I'm not going to downplay the work that goes into actually training these bigger and bigger models, because it's not just, oh, let's add on some more parameters and that's it. There's still some work involved in how do we practically train this model. So there's some little things here and there you have to do to kind of make the training process more efficient. But the idea is it's still the same of like, hey, let's brute force our way to AGI. Just these bigger and bigger neural net models, hoping that somehow this morphs into some smart AI system. That may be the answer. Who knows? Maybe I personally don't think that's the only path forward. I think it's a easy path forward. But I'm sort of wary on whether it's the right path forward, to be honest. Yeah, I personally agree that if you can do whatever you're doing with less hardware, less resources, less parameters, if you can accomplish the same thing with less parameters, then I think that's more of an algorithmic advancement than simply just adding on more parameters onto a model. Yeah, but then again, maybe the simple solution is the correct solution. Um, but yeah, it's yeah, it begs the question as to the same thing, right? That I mentioned. If that is the answer towards AGI in terms of just like scaling these larger language models, do you guys think that AI research is becoming more inclusive or less inclusive?
Well, if scale is the answer, then definitely less inclusive, because there's only a select few labs in the world that have the resources to train stuff at that scale. I mean, I'm sure that not even a lot of countries would be able to justify spending that much money on GPU or TPU clusters.
Yeah, it would definitely, as like for all the same reasons that he just said. Um, with what NASA was doing with their space development, or that kind of plateaued at a certain point. But then Elon kind of in some new ideas of how to get it done and was able to do it for much cheaper. Um, I think this is just a case where they're throwing a lot of money and resources at it, and it's reaping like good results. But at the end of the day, as you said, the hallmark of the brain is its efficiency. So, um, yeah, I don't know how that would play out. I don't know if it's a lack of the understanding of the brain that's causing it. But it doesn't really seem similar to how their brain operates.
Okay, so if it is scalable is the answer, wouldn't they work up on a point of diminishing returns, right? Because they always work on diminishing returns if you're doing scaling issues.
That's a good point. I think they had even mentioned that in the paper in terms of 'cause I mean, yeah, that's a big thing that anytime we're talking about like the scaling, there's a whole consideration of diminishing returns. Basically, as you go further and further, the increases basically in performances get less and less. So it looks more logarithmic than say exponential or linear. Um, they've actually, I think in the paper, according to them, that the graph is seeming more linear rather than logarithmic. So there is a well, there is a possibility based on what they're seeing so far that at least for now, with increases or in scale, there should be better and better results. Now, one may ask, how are they actually judging? What's their metric for really judging if this thing is getting better and better? Yeah, is it really a good metric of whether we've, achieved a system that we can say is an AGI? Because one of the hallmarks of AGI is the ability to do multiple tasks of different types. So the idea of a general intelligence, essentially, sort of how a human can basically learn multiple tasks from different modalities. Um, is AI or is current AI research going along that path? For a long time, I would say no, because most of the models are basically very specific to some domain. So basically, if you're doing some sort of AI model, it's either in the language domain or the vision domain, or maybe like a reinforcement learning domain, but something that can like work across all multiple domains, multiple different types of tasks. I have not seen a lot of work like that. Now, recently, and I guess this takes us into the other model that Google was working on. Is this one, Gato. So basically, this idea of like a general agent that can do multiple different tasks. So essentially one model that can do multiple different tasks. So Google basically, or DeepMind, basically try to tackle this problem. So it's basically try to see if they could use one model with one set of weights. So basically, it's not like it's retrained for each different task, but one set of weights to see if it can be used for multiple different tasks from multiple different modalities. Um, and they got some impressive results here, meaning it got reasonable results in all different tasks. It didn't get state-of-the-art results in each of those tasks, but it got reasonable results. And again, this used a transformer architecture. Essentially, it's found some way to more or less turn these tasks into some form of sequence. Yeah, basically convert it into some form of sequence and then train the transformer architecture in that way. But yeah, it was able to more or less manage in all of these different tasks. So I guess the question becomes, do you guys think that AGI or future AGI system will require the use of basically one unified model that can be used across these different types of tasks? Or will it look more like different types of models that can work for specific tasks?
I think it would look like the more specific models for different tasks.
Mm-hmm.
Because even the human brain can't do everything perfectly. It's always a specialization. If you're good in maths, languages, memory, it's not the human brain. Even the human brain is never good at everything at one time. So I think the way is different, not different models for different tasks.
I think it would be both. Like, I think there's applications for both because the brain is good at both. The brain takes a lot of shortcuts, and there are certain cognitive tasks that are very similar. But yeah, there are areas where specializing wouldn't hurt. And then when specializing, like, you have different degrees based on how much computing power you throw at it.
All right. Anybody else or?
Well, the different areas with the different each different area, I think is where we're finding a lot of industrial value today, and that's ever necessarily going to go away. But I would like to see a single model that can do everything by itself, although it's probably not realistic since like the brain is improving that different sections of the brain handle different types of tasks. Like the vision center in your brain is different from your the part of the brain that governs your motor skills. And it would be nice to see one general model that can do everything pretty well.
Yeah, I'm kind of coming from the perspective where at some point there will be something this similar to the brain, but designed better than the brain. Just because at the end of the day, it's just neurons, but they all fire differently in different areas. But at the end of the day, it's just neurons. So I feel like at some point when our understanding is high enough, um, general would be pretty possible.
I see. Well, okay. So I guess in a way you're kind of using the airplane analogy where, you know, airplanes today, they might have been originally inspired by birds, but obviously the current design isn't trying to model how birds exactly fly. It's probably better. So there's that. So, you know, there have been arguments that the same thing could apply to AI, where yes, as it stands, we're using the brain as a form of inspiration, but as time goes on, you know, practically, you know, what turns out to be AI may not look anything like the brain. May have been originally inspired by the brain, but you know, the end product may not look like the inner workings may not work anything like the brain, which may be fine at the end of the day, because again, if we have some metric that we're judging or evaluating this thing on and it's doing well, I would say, okay, that metric is a good metric. Then why does it need to be exactly right? It doesn't matter. At the end of the day, it does what it's supposed to do, right? A plane does what it's supposed to do. It doesn't matter if it flaps its wings. At the end of the day, it flies you from one destination to the next. So that's all that should matter at the end of the day. Of course, there are the people that, you know, the purists were like, you know, if we're gonna create AI system or a AGI system, it's gonna have to basically model the brain or how the brain or the reason why we haven't created an AI AGI system is because we don't fully understand the brain, and that's the problem, and not something else. So there's always that discussion or argument that people like to make. But yeah. I mean, one thing I can definitely say is I've been pretty impressed by generally the transformer architecture overall, or the, you know, attention architecture. Over the past few years, yeah, it started out with just language modeling, but it's now being used for vision. But basically being used for all areas of AI, machine learning. So it's promising that, you know, there may be that vision of basically using one single unified model for, you know, all these different tasks. I mean, practically, I honestly I think if we are to create AGI, it's probably going to have to go along that route. Maybe difficult to see how it will happen, but it probably will have to go along that route in some way. Along that discussion of, you know, whether we want a unified model or if it's basically pieces of specialized models. There's this section here of the article that basically stood out to me. So it's saying your single brain style models have interesting connections to neuroscience. Mountcastle famously stated that the processing function of a neurocortical module is qualitatively similar in all neurocortical regions. Put shortly, there is nothing intrinsically motor about the motor cortex, nor sensory about the sortal cortex. Mountcastle found that the columns of neurons in the cortex behave similarly, whether associated with vision, hearing, or motor control. This has motivated arguments that we may only need one algorithm or model to build intelligence. There's this book that Jeff Hawkins wrote. I think it's called Thousand Brains Theory or something like that. But it talks about this whole notion of a neurocortical column. It's just saying that the brain is made up of these neurocortical columns, and all of them more or less are the same algorithmically. It's really just you know, just because, you know, even though you have parts of the brain that are specialized, like, you know, vision, the motor region, all that stuff, the actual things that make up those parts of the brain aren't very different from each other. So there is a theory that we could just need to find that basically that the algorithm for that single unit, and to create the brain, it's really just replicating that unit in different ways. Or it's basically maybe how it's arranged, but basically everything is made up of that single unit. And we simply just need to find the algorithm for that single unit of intelligence, essentially.
Yeah, and based on that, because machines don't have biological limitations, they could model something pretty cool off of that.
Yeah. Okay. All right. So I guess to kind of finish up the discussion, so I mean, let's talk in terms of timelines. So basically, based on what you guys are seeing, like realistically, because I mean, as I said, there have been a lot of clickbait articles out there saying, AGI is right on our doorstep. So basically, just a few more steps and we're there. So, what do you guys think? Do you think we're that close, or do you think maybe they're kind of jumping the gun here, that we're a lot further than we are? I mean, it's a lot further away than we think it is.
Well, I think it's further away, but not too further away. So the articles may be over exaggerating, but I think we're kinda there, almost there.
I don't think we're there yet, or I don't think we're near yet, because I think that there's still I look at it, and I think that until the accessing it on a daily basis, like tapping into some cloud AI infrastructure, or using the processing power of the phone, and then some amount of processing going on the phone, and then being sent back to the AI, and then like billions of people doing that. I think that's when we'll get to that point. I just don't think we're there right now. And I don't see that happening for another like 5 to 15 years.
Timelines
5 to
are
15
kind of
years kind of close,
yeah, there's that too. But timelines are kind of difficult because I mean, the given the improvements that we've seen over the last 10 years, like since deep learning was basically repopularized, have been ridiculous. But at the same time, I don't really know if we have any quantitative measure of the distance between where we are now and AGI. So it's pretty hard to say. I'd give it sometime within the next 25 years or so.
I kind of measure it against like the virtual reality space. I think when a lot of people are very plugged in like that, I think that's when you start to see like those massive leaps. Because we know like technology improves at a very fast rate, but there's always like events that trigger, like even if it's just for a year, like very rapid development. I think that virtual reality is that space for AI specifically.
Yeah, I kind of agree because what do you call it? Yeah, the VR. I don't think that you can ever truly have AGI without some form of embodiment. Like without like some avatar that's interacting with the world in some way or another. So definitely, I think that VR Like if they end up training agents in VR, there could be a point where we wouldn't be able to distinguish a virtual AI agent from another human. And I would probably say that that might be when we reach AGI-ish.
Okay. Sorry to cut you guys, but the meeting time is running out. But yeah, it sounds like some very good discussions.